Section: Introduction. We're going to talk about how large language models, LLMs, have made significant strides in recent years. One of their most impressive features is their ability to learn new rules from just a few examples. For instance, if we give a model a couple of examples like, apple leads to red, lime leads to green, and then ask it about corn, it will correctly respond with yellow. This ability, known as in-context learning, ICL, has been used extensively and has produced some impressive results. But what's the science behind this? How does the model use the examples and the question to come up with the right answer? To answer this, we're going to use the concept of a hypothesis class from statistical learning theory. In simple terms, a hypothesis class is a set of functions that operate on an input and are defined by a set of parameters. For example, if we're dealing with real numbers, the hypothesis class could be a set of linear classifiers, defined by a parameter vector and operating on the input. The goal of learning algorithms is to find a function within this class that fits the training set well. This is known as empirical risk minimization and is a key concept in supervised learning. However, it's not clear if ICL works in the same way. This is because the prediction is made using a combination of the examples and the question, which is typically processed by an autoregressive transformer. This could be any function that uses the examples and the question to produce the output, including non-parametric methods like nearest neighbor. Recent studies have started to explore this question. For instance, one study showed that when training a transformer from scratch to perform linear regression in context, the emerging learning algorithm is similar to stochastic gradient descent. But when it comes to LLMs performing more complex natural language tasks, it's not clear what the hypothesis space might be. In our work, we show that for a wide range of tasks, ICL in LLMs can be seen as working on a very natural hypothesis space. We propose that the transformer maps the training set into a task vector that essentially represents the rule described in the training set. Given the transformer and a vector, we can construct a new function that implements the task. This function is very similar to the original transformer applied to the question without examples but instead modulated by the task vector. Our view is also related to soft prompts, as both approaches use task vectors and soft prompts to guide the function of the transformer towards a specific task. However, in ICL, task vectors are calculated in the forward pass rather than being fine-tuned. Our contributions include proposing a hypothesis class-based mechanistic view of ICL, and conducting experiments to validate our view on a range of publicly available LLMs and a diverse set of tasks. Our results further the understanding of ICL and may have practical implications for the efficient adaptation of LLMs to perform specific tasks. We're motivated by the hypothesis class view of learning theory, and our goal is to understand if ICL maps the set of examples to a function on the question and how this mapping occurs. Specifically, we want to see if ICL converts the examples into the parameters of a function within a certain hypothesis space. Our empirical findings suggest this view is applicable, shedding light on the structure of the hypothesis space on which ICL can be viewed to operate. We use a decoder-only transformer LLM, a set of examples used as input to ICL, and a question that ICL is asked to provide an output for. To show that ICL operates within a hypothesis space, we aim to show that its underlying mechanism can be broken down into two parts: a learning algorithm that maps the examples into a task vector, independent of the question, and a rule application, which maps the question to the output, based on the task vector, without direct dependence on the examples. Thus, we consider the following mapping from a set of examples and a question to the predicted output. The output of ICL on the combination of the examples and the question equals the rule application of the question and the learning algorithm of the examples. If we can break down the forward pass of the LLM into the above two components, we can view ICL as operating on the following hypothesis class: the set of all rule applications of a variable and a parameter. In the next section, we propose an implementation of such a class. Section Summary. Large language models have the ability to learn new rules from just a few examples, known as in-context learning, ICL. In this work, the authors propose a hypothesis class view of ICL, suggesting that the transformer maps the training set into a task vector that represents the mapping described in the demonstrations. They validate this view through experiments on various language models and tasks, contributing to a better understanding of ICL and its potential practical implications. Section: A proposed hypothesis class. We're proposing a new way to look at a certain type of machine learning model. There are many ways to implement this model, but we're focusing on one that's based on the transformer architecture. Imagine a scenario where we have an input that ends with a question, for example, corn, followed by an arrow symbol. We see the learning process as two steps. First, we calculate a set of parameters based on the training data, and then we apply these parameters to the question. One way a transformer might do this is by using the first few layers to calculate the parameters, and then the remaining layers to take these parameters and the question as input and produce an output. However, this presents a challenge because the transformer can access the training data and the question at any layer. In the following sections, we'll address this challenge and present experiments that support our view. Specifically, we'll show that we can isolate the two steps of the learning process in the forward pass of the model. We'll also show that the parameters we calculate are meaningful and correspond to learned tasks. We first demonstrate that separating the forward pass into these two steps maintains the high accuracy of the model. However, there are some challenges. For example, the initial layers that calculate the parameters can attend to the question, which means they might depend on the question. This creates an unwanted dependence of the parameters on the question. To solve this problem, we introduce a dummy question and calculate the parameters using that question. We then use these parameters as input for the remaining layers. We also propose a procedure to calculate the output without allowing direct dependence on the training data. To isolate the two steps in the forward pass, we dissect the network to eliminate unwanted information flow. If the model's performance is maintained after this dissection, we consider our approach validated. We hypothesize that the first few layers generate the parameters without depending on the question. Simply blocking attention to the question in these layers resulted in poor performance. Instead, we replace the question with another question, making the hidden states independent of the question while preserving the structure of the prompt. The remaining layers after the initial ones have direct access to the training data in the regular forward pass. To prevent these dependencies, we propose to forward the transformer only on the question and the arrow symbol, excluding the training data. We test our approach on a diverse set of 18 tasks across 4 categories: algorithmic, translation, linguistic, and factual knowledge. For simplicity, we limit ourselves to single token outputs. We use multiple open language models for our experiments. Section summary. The proposed hypothesis class involves different choices of A and F, with a focus on the transformer architecture. The challenge lies in separating the forward pass into two components, A and F, while maintaining high accuracy. To address this, a dummy query, X, is introduced to calculate the representations of right arrow and create bold symbol, theta, while the remaining layers only access X and right arrow to calculate F, X, bold symbol, theta. By dissecting the network and eliminating undesired information flow, the components A and F can be isolated in the forward pass, validating the proposed mechanism. Section: Finding. In the section we're discussing, we're looking at a mechanism we've previously described. This mechanism has a variable element, which we'll call layer L. This is the point where one part of the mechanism, which we'll call A, ends and another part, F, begins. We've tested this mechanism with different values for L to see which one works best. We've done this by measuring the accuracy of the mechanism on a development set. Interestingly, we found that all models performed best at a similar intermediate layer, regardless of their individual parameters and the number of layers they had. Next, we compared the accuracy of our mechanism to that of a regular forward pass, which is a common method used in this field. We tested 3 different procedures. 1. The regular procedure, which applies the model to the demonstrations and query. 2. Our proposed procedure, where A generates a parameter vector using a dummy query, and F is applied to the query by running the transformer with the parameter vector patched at layer L. 3. A baseline procedure, which is a forward pass of the model only on the query, without demonstrations. We found that our procedure maintains around 80 to 90% of the accuracy of the regular procedure, while the baseline procedure only reaches 10 to 20%. This suggests that our proposed separation of A and F is a good approximation of the process underlying the regular procedure. We also looked at the robustness of the parameter vector, which is derived from the demonstrations and a dummy query. We wanted to see if it would remain stable across different demonstrations and dummy queries. To test this, we generated 50 task vectors per task with varied demonstrations and dummy queries and conducted 2 analyses. First, we used a dimensionality reduction technique to show that the task vectors form distinct clusters, each containing task vectors of a single task. This suggests that they encapsulate task understanding. Second, we looked at the variability of the task vectors. We found that vectors within the same task are closer than those between different tasks, indicating that the parameter vector is stable within tasks and not highly influenced by the dummy query or demonstrations. We also found that even when the last token can attend to the demonstrations, the model mainly uses the task vector, without directly accessing the demonstrations. This was confirmed by a test where we provided the model with demonstrations for one task, but injected the task vector for a different task. Finally, we found that the learned parameter vector captures information about the task demonstrated by the demonstrations. We confirmed this by examining the top tokens in the distribution over the vocabulary induced by the hidden state. In multiple cases, we observed tokens that directly describe the task. This supports our view that the parameter vector carries significant, non-trivial semantic information about the task. Section summary. The authors explored the impact of different choices for the layer where the mechanism ends and the function begins, finding that all models exhibited a performance peak at a similar intermediate layer. They compared the accuracy of their proposed mechanism to a regular forward pass and found that their procedure maintained around 80 to 90% of the accuracy, while the baseline reached only 10 to 20%, indicating that their proposed separation of the mechanism provides a good empirical approximation of the process underlying the task. Section: Emergence of ICL. Let's delve into the emergence of ICL, or in context learning. One of the main questions we're trying to answer is how ICL develops as a skill during the pre-training phase of language learning models, or LLMs. Some studies have shed light on this, emphasizing the crucial role of the structure of the training data. These studies have used a combination of probability-based analysis and hidden Markov models to theoretically explain how ICL comes about. They've also conducted empirical research to understand the impact of various distributional properties of the pre-training data. Now, let's talk about the role of meta-learning in transformers. Several studies have focused on how transformers can be trained from scratch to perform basic tasks, like linear regression. They've drawn theoretical comparisons with algorithms such as gradient descent, showing how transformers could potentially implement these algorithms. A common assumption in these studies is that there's a known parameter space where gradient descent can function. Our research aims to identify such a parameter space for LLMs. Moving on to the role of ICL in LLMs, some researchers have pinpointed induction heads in transformers as a probable primary mechanism of ICL. They've provided empirical proof linking ICL to gradient descent in LLMs, with a particular focus on classification tasks. At the same time, other researchers have been studying a phenomenon similar to the task vectors we're examining. In this phenomenon, a single vector can encode learned functions. Our discoveries complement theirs, and we believe future research could delve deeper into the relationship between these two phenomena.